Hello everyone, here we'll be discussing the introduction to differential equations. Here we'll mainly be discussing some vocabulary and definitions that we'll be using throughout the class. I won't actually show you any techniques really, but I'll explain how we can kind of check our answers for certain cases and specifically what we're dealing with here. So first off, an ordinary differential equation is an equation consisting of derivatives of a function in one variable. So the function will be of one variable. If you have a function of two variables, then of course you can take partial derivatives, in which case you'll deal with what are known as partial differential equations. Now, ordinary differential equations are very often referred to by the acronym ODE, of course, where PDE stands for partial differential equations. We actually won't really be seeing any of those in this class, maybe a little bit when we deal with exact equations, for instance, but more on that way later. For right now, let's just consider this equation. We have y double prime plus y prime equals 2y. So notice this is an equation involving derivatives of the function y. So we're assuming y is a function of some other variable, let's say x. Now it doesn't say that anywhere, so it's up to us to determine what the variable is and what we want to call it. Usually we'll use y and x, but we could use x and t, for instance. X could be a variable of t, or a function in terms of t, I should say. Now I'm going to show you what a solution of this is. But it may not be actually the only solution, as we may see later on. But let's just say y is equal to e to the x. Now that definitely works because notice, how do I know this works? Well, if you take the derivative y prime, you get e to the x itself. And then if you take the second derivative y double prime, you also get e to the x. And if we compare the left-hand side to right-hand side, so RHS for right-hand side, that's y double prime plus y prime. If we use what we have here based on this supposed solution, this is e to the x plus e to the x, which is equal to 2e to the x, of course. If we compare this to the left-hand side of the equation, which just says 2 times y, and also using this supposed solution, y is equal to 2 to the x. So that actually certainly works, because since y is 2 to the x, we get, or e to the x, we get 2e to the x. And notice these match. The right-hand side is equal to the left-hand side, so we verified that this works. If we take the second derivative of this plus the first derivative of this, we get 2 times the original function. Now, this is not the only scenario. I'm going to show you something, but as it turns out, what I'm about to show you kind of works in general a little bit. If you have a constant multiple of this, it will actually also work. So for example, what if we had, let me just kind of border this off for a moment. What if we had y is equal to c e to the x? Well, then notice y prime and y double prime will also be c e to the x because of the constant multiple rule. And when you add y double prime to y prime, you just really get this added to itself because they're all the same in this case. And that works because you'll have c e to the x plus c e to the x equals 2 times that. So that's obviously the case because its derivatives look like itself. Now, that is a feature of e that is kind of going to be showcased a lot in this class, but there are other ones we'll be exploring a little bit with another example right now, so let's take a look at that. All right, here we'll be taking a look at two examples. The first example is kind of similar to the previous one we saw, only this has the fourth derivative involved, where this only has the first derivative, and here we're asked to show that this is a solution. So they're giving us the supposed solution. It's up to us to check to see if that is indeed a solution or not. With the previous example, we had the second derivative involved. The highest derivative here is 4, and here the highest derivative involved is 1. Now the highest derivative in a differential equation is known as the order of that differential equation. So here this is a fourth order differential equation, this is a first order, and the one we saw in the previous example was a second order differential equation. And we'll discuss other terminologies like that later on after these examples. But for right now, let's kind of look at this and see if we can, based on what we saw in the previous example, see if we can find some pattern recognition here. Now this says the fourth derivative of some function is equal to itself. Well, we know from what we saw previously that c times e to the x, a constant times e to the x, has derivatives that are itself. So the first, second, third, and so on derivatives are actually equal to y. So this actually does work. This is definitely a solution. But it is actually not the only one. There is another solution that works in this particular instance. They may not be very obvious, but I'll show you. And it is y equals sine of x. In fact, y equals cosine of x also works. So let me just kind of show you that if you were to take derivatives of this, the first derivative, y prime, is cosine. Second derivative, y double prime, is negative sine. Third derivative, y triple prime, is negative cosine. And then finally, fourth derivative is back up here. So if you were to take the fourth derivative, you get back to y, which is sine of x. And the reason that's true is because derivative of cosine is negative sine, so you get the double negative, which is positive sine. And believe it or not, the same is actually true for cosine. If y is equal to cosine of x, then if we take its first, second, third, and fourth derivatives, by the way, this prime notation can be replaced with the number of primes you want in parentheses. I generally like to use that for 4 and beyond because there's too many primes, it looks like. Triple prime I think is the most, but you could use 3 if you want. It's just up to you really. So derivative is negative sine, derivative of negative sine is negative cosine, derivative of negative cosine is back to positive sine, and then derivative of sine is back finally to cosine. So it is indeed true for both of these, its fourth derivative is equal to the original function. And, kind of like we saw here, we can multiply these by constants, and even further, we can actually add those, believe it or not. So another possible solution is c1 times sine of x plus c2 times cosine of x. And this should be fairly obvious why this is true. If you take the fourth derivative of this, it's the same as taking fourth derivative of each of these, and we know what those are, they're back to themselves. I haven't shown this with constant multiples, but by the constant multiple rule, the constant multiple comes down for free each time. So all of these 4 are actually examples. This, believe it or not, is the most general example, and why this is a general example and not this, we'll actually see that a little later. There's a connection, believe it or not, between these two. Now, for this one, we want to show that this is a solution to this differential equation. We'll have to use what we did last time by checking with the right-hand side and left-hand side. So for the right-hand side, y prime, well, let's take the derivative of our supposed solution. For this, we need quotient rule. It's going to be all over the bottom squared. And what I'm going to do, I hope you don't mind, is off to the side, I'm going to figure out what the numerator is from quotient rule. If you don't remember, quotient rule basically says, let me write QR for quotient rule. It says that the derivative of a fraction is equal to the derivative of the top times regular of the bottom, minus regular of the top, u, times derivative of the bottom, u prime, all over the bottom squared. So in this particular case, we have, let's see, derivative of the top is going to be c to the x, regular of the bottom is 1 minus c to the x, minus regular of the top, 1 plus c to the x, times derivative of the bottom, which is now negative c e to the x. And look at that, we have a double negative situation here, right there and there. And actually, if you distribute this and distribute this, maybe we actually don't even need to distribute. Let's actually, instead of distributing, let's do this. It's a little less obvious, but we can definitely do this. We can actually factor c to the x out. What we have left on the inside is just these two added to each other, which is 1 minus c to the x plus 1 plus c to the x. And I haven't even written the denominator yet, which is the original denominator all squared. So it's going to be all over the bottom squared, which is 1 minus c to the x all squared. That's 1 minus c to the x all squared. And notice up on top, the c to the x is canceled, so we get 1 plus 1, which is 2. So this is actually all equal to 2 c to the x. Wow, nice. So that cleaned up quite a bit there. And that was the right-hand side. Now checking with the left-hand side, this is going to be a little bit to check as well. But the left-hand side is 1/2 times y squared minus 1. So 1/2 times, let's see, y squared, y is this. If you square this, it's going to be the top squared, which I'll actually do off to the side here. And you know what? It actually won't be too bad to verify that this will be true for both plus or minus. So when squaring the top or bottom, you kind of get the same thing, kind of. So recall for squaring a binomial, you get the first one squared, 2 times their product, depending on the sign in this case, and then the last one squared is c squared e to the 2x. Now the last one is indeed positive no matter what, because whether this is a plus or a minus, when you multiply it by itself, it'll still be positive no matter what. So, okay, is that helpful at all? Well, let's see. So for the top case, we're going to get 1 plus 2c e to the x plus c squared e to the 2x. For the denominator, I'll actually just leave it as 1 minus c e to the x all squared. And the reason why I'm doing that is because I can kind of tell that we have that here, so I want to compare apples to apples, so to speak. And what I haven't written is this minus 1 part yet. But minus 1 I'm going to actually write as, well, this denominator over itself. So to do that, I'm going to notice the negative version of this is going to be 1 minus 2c e to the x plus, I need to erase for space there, sorry about that, c squared e to the 2x all over the same denominator. 1 minus c e to the x all squared, just like that. So now, of course, this is minus, but when you distribute this negative into the top, all of the signs change like this. When you combine into one fraction, notice the 1's cancel, the c squared e to the 2x's cancel, and what we're left with now here is actually 2c to the x plus 2c to the x. Notice that's, of course, just 4c to the x. And when you multiply that by 1/2, it indeed matches with this, because 4 over 2 is just 2. So that's 2c to the x all over this common denominator. So I didn't really show too much of the work there, just because of space and whatnot. But they are indeed the same, in which case this is indeed a solution. So we have shown what we were asked to show. So now let's carry on with some more vocabulary. Alright, so here's some terminology that is often used with differential equations. We say a differential equation is linear if only known functions of the variable are multiplied to the function in question. So what do I mean by this? What I mean by this is you could have something like, let's say, y double prime plus xy equals 3x squared, something like that. So the only things multiplied to the function, or even derivatives thereof, is a known function. You cannot have something like y times y prime, or something like, let's say, y double prime times y to the third. Or even y double prime squared, that's not good either, because y double prime squared is y double prime times y double prime. So we have a unknown function multiplied to another unknown function, basically. So only known functions can be multiplied to the function in question, or even derivatives of. So let me just say, to sneak in here, derivatives of. So we could say derivatives of the function in question, as well as the function in question. So like here, we could have a 2 multiplied to y double prime, and that's considered linear. But if y is multiplied to y prime or y double prime, that is non-linear. Okay? Homogeneous means that the only non-zero terms in an equation are derivatives of the function in question. So actually, the only problems we have seen so far, the only examples we've seen, that is, were actually homogeneous in some sense. Usually homogeneous is discussed whether 0 is on the other side or not, but specifically what this means is that you have something like this. For example, y double prime plus y prime plus y equals 0, that's an example of a homogeneous equation. And again, yeah, homogeneous usually means equal to 0, but specifically for differential equations, we want only the non-zero side to contain only terms that involve derivatives of the function itself. In this case, of course, the function is y, where our variable usually is x, like I previously mentioned. So for example, y double prime plus xy prime equals sine of x. This is a non-homogeneous equation. Much like terms involving these terms mentioned up here would be non-linear equations. Okay? So that's just a terminology we'll be seeing in future videos. And what else can I say about this? Oh yeah, so these are non-zero terms, like sine of x, a non-zero term that is not it's not the derivative of the function itself, or multiples thereof. So yeah, essentially we can have these so-called linear terms that involve derivatives of the function itself, like x times y prime is okay, but sine of x, that's not a multiple of the function itself, or derivative of that function. So really when I say are derivatives, I should say are multiples of derivatives. And when I say multiples, I mean that we can possibly have x multiplied to y prime, for instance, or e to the x times y double prime, or something like that. So that would be homogeneous so long as you don't have a term that does not involve that. So here this is non-homogeneous, but here this is homogeneous. Okay? An initial value problem is a differential equation with an associated initial condition, or possibly more than one initial condition. And what an initial condition is just an evaluation of the function in question. And this is normally used to solve for any unknown constants. So kind of like we saw in the previous example, we were asked to show that something involving c was a solution to a differential equation. We'll do an example right now, which will be the same question, but it will have an initial value, initial condition that is associated with it. So we'll actually see an initial value problem that corresponds to the previous example we saw right now. Right, so I think these last examples here will actually end the video, but let's take a look. So I want to solve this differential equation given this initial condition. And what we can kind of notice here is, again, the variable x is nowhere in sight. So we're just going to assume that the variable is called x, and this is a function of x. So y of 0, for instance, just means if y is equal to a function f of x, then f of 0 is equal to 2. So this kind of shorthand notation. So y is equal to y of x. So just to write that over here, y is defined to be, so that colon in front of the equals means defined to be, y of x. In other words, you can replace y with y of x if you want, but since it looks like y multiplied by x, we tend to only use this for initial condition purposes, if that makes sense. But anyways, we actually know the solution to this from previous example, right? This is 1 plus c e to the x over 1 minus c e to the x. Now, if this is a solution, and we have this initial condition, we can actually solve for these constants c by letting x be equal to 0. So let me just show you, when x is equal to 0, we end up getting y of 0, which is 2, so we'll use that sooner or later, equals 1 plus c e to the 0 over 1 minus c e to the 0. Now, of course, since e to the 0 is 1, this becomes 1 plus c over 1 minus c. And now all we have to do is, well, solve for c. And there are actually multiple different ways of doing this. I want to see if there may be a clever way of doing this that I can see off the top of my head. I can see something, but it's not worth it to go over. So let me just do this. Let's cross multiply. So we're going to get 2 times the quantity 1 minus c is equal to 1 plus c. Distribute this guy. We get 2 minus 2c is equal to 1 plus c. And then if we add 2c to this side and subtract 1 to that side, we get 2 minus 1 is equal to 2c plus c. So I hope we see what I'm doing. I subtracted this 1 to the left and added 2c to the right. Not to interfere with the next example too much. That's 2c. Perfect. So we end up with 2 minus 1 equals 2c plus c, which of course is just 1 equals 3c. So that means, I keep writing x, sorry about that. Old habits, I guess. So then dividing by 3 gives you c is equal to 1/3. That is not our answer, but it actually tells us what our solution is based on this value. So if we replace all of the c's in the original solution with 1/3 now, then this will now be the solution to the initial value problem. Awesome. But it depends very much on this initial condition. So I hope we see that in the terminology we established from the previous screen. Okay. Now here we have a very, very similar thing, but it's a little different. There are actually 2 initial conditions here. So here we want to solve this crazy differential equation. This is a second order linear homogeneous differential equation based on the terminology we've established. Good. So y double prime minus 2y prime minus 3y equals 0. Y of 0 is 0, y prime of 0 is 3. Given that this is a solution. Now if you want to verify this is a solution, just take the second derivative, first derivative, and well, apply the left-hand side and you'll get 0 actually, no matter what C1 and C2 are. But specifically with these initial conditions in mind, we actually have to find C1 and C2, which is not that bad actually. If we were to, let's say, plug in x equals 0 into this as is, let's see if we can do that. We get y of 0 is equal to, replace x with 0, you get C1 plus C2. And that's, of course, because when x is 0, e to the 0 is just 1. And then, you know what, in order to discuss y prime is 0, let's find its derivative y prime. So that's going to be 3c1 e to the 3x minus c2 e to the negative x. This is by chain rule, derivative of e to the 3x. We multiply it by the derivative of the power, which is 3. And e to the negative x has derivative itself, again, but by chain rule, derivative of the power negative x is negative 1. So we get multiplied by negative 1 there. So now, with that being said, when we plug x being 0 into that gives us y prime of 0 is equal to, again, when x is 0, the e to the zeros are 1. So we get 3c1 minus c2. And specifically, we know what y of 0 and y prime of 0 are. In our initial conditions, they are, well, 0 and 3. So we get 0 is equal to c1 plus c2, and 3 is equal to 3c1 minus c2. So yes, this is a system of equations. In this case, we can solve by elimination. We get 3 is equal to 4c1, so that means c1 must be 3/4. And if you look back at this original equation before we canceled the c2 out, if you were to subtract c2 to the other side, you get c1 is equal to negative c2, in which case c2, or I guess I should write it the other way around, c2 is equal to negative c1, that looks a little better, in which case c2 would then be negative 3/4. Perfect. So now what does that tell us? It tells us our solution to this initial value problem must be y equals c1, 3/4, e to the 3x, plus c2, which is negative 3/4, e to the negative x. Perfect. Now it's just up to you to check that it is indeed a solution and it also satisfies these initial conditions, and we could do the same thing for the previous example up here. Awesome. So like I said, that concludes the video. This is just a quick intro. So I hope we enjoyed and understood everything we discussed here. And I'll see you in the next videos where we'll be discussing more techniques on differential equations. So thanks for watching, and I'll see you then.